webinar and the talk that I want to have with you today is about the course that I recently released, but I want to give like a high-level overview of what I will describe in the course and like highlight the main issues and main design choices and how the components work together and so on. Basically, this is the interesting part and not the little details that you uh, further have to learn on your own. Okay, so let's start. And yeah, the course is called the Full Stack 7 Steps MLOps Framework, and as you will see, there are 7 steps that usually you want to uh, implement to have a successful ML system. Yeah. Okay. So the goal of this talk will be to give you initially an overview of a batch architecture. Afterwards, I want to drill down into all those components of the batch architecture. Basically, these are those 7 steps that I've been talking about. And afterwards, I want you to show you how easy it is to adapt a batch architecture to an online ML system. And I will also highlight what's the difference between a batch architecture and an online ML system. And this talk is mainly for software engineers, data scientists, data engineers who want to transition or want to get some extra context about machine learning engineering and MLOps. Because even if you're not directly working on the machine learning engineering component, it's always good practice and it's always good to know and get a feeling of the big picture, because most probably you will work with a machine learning engineer, so it is good to understand basically what it wants from you, right? So you can collaborate with people with this. And yeah, and also if you're a machine learning or MLOps engineer, like an entry or mid-level machine learning engineer who want to level up, this is also a great presentation for you. Okay, so let's get started. So let's start, as I said, with a generic overview of the batch architecture, right? So yeah, as I said, a standard batch architecture has 3 components and is usually based on this 3 pipeline design, which almost always consists of a feature engineering pipeline, of a training pipeline, and a batch prediction pipeline, or more generic, the inference pipeline, basically where you get your model and use it in production, right? So the feature engineering pipeline sits on top of this data source. It can either be like raw data source or cleaned and prepared data source from previous data engineering pipelines, right? And this depends usually on the scale of the project. If the project is bigger, it means you have a data engineering pipeline and your data is prepared. If not, it's kind of your job to do that, right? This feature engineering pipeline can, again, depending on the context, can be implemented in plain Python, can be implemented in a distributed system using Desk, Spark, and so on. Again, it depends a lot on your specific context. Afterwards, the training pipeline, again, can be implemented in PyTorch as a deep learning model or in Desk as a distributed model. Again, it depends on your context, right? And yeah, so we have these 3 pipelines. So after the training pipeline, the output will be a model artifact, which basically represents the weight of your trained model, which at the end of the day is just a file, which is saved. And afterwards, in the batch prediction pipeline, you load this model artifact and you do the predictions, right? But the difference between like a classic, a RESTful server and this batch prediction mode is that you get all of your data of interest and you run your model on top of it. For example, in a recommender system, you do the cross product between all your items, let's say between all your movies and users in your streaming platform, right? So basically you cache recommendations for all your users into a storage, right? You compute the recommendations for all your users, and afterwards you take those recommendations and cache them into a storage. Again, the storage can be an S3 bucket, Redis, BigQuery, depends again a lot on your specific application. And yeah, basically now you have your predictions already computed and they're ready to be served in a consumer app. This consumer app can be a simple superset dashboard, a RESTful API, a front end, basically any web app, mobile app, dashboards, anything. It can be anything because it can be accessed very easily, right? So now let's see some variations of this batch architecture. A first variation is where you do kind of an online training. For example, in this course that I have done, I'm using this setup. Why? Because my real-time data source is represented by a time series, right? And when you train a model on a time series, if you train it until the present moment, you can do predictions based on data until the present moment. And if, let's say, one day passes by, that model will already be obsolete because usually when you train a model on time series, you want to forecast in the future. And you always want your model to be trained until the present to be able to predict the future because time series are always changing a lot and you can't generalize very well. So you always want your model to be trained until the present moment when you can predict in the future. Which means that when you ingest new data, it makes a lot of sense and you're kind of obligated to train your model on this new data, which are represented by time series, so you can make new predictions. So basically everything is the same as I explained before, but the main steps are like this. So you have a real-time data source, you do your feature engineering, you train your model based on the configuration that you found during the experimentation, you have your model artifact, and afterwards you trigger the batch prediction pipeline, you do your, in this case, you do, let's say, the forecast for the next 24 hours. In the course, we use this example of where we used energy consumption levels across Denmark, and we always predicted the energy levels for the next 24 hours. And the data had a granularity of 1 hour. So basically, we forecasted 24 data points into the future. So here we forecasted for every time series the next 24 points. And afterwards, we save those predictions and these are ready to be consumed. And there's also this offline training setup where here you can see two branches, right? So you have this static data source where you basically it's your classic training data set that most of you are used to, right? So you have a data set, you prepare your data, you train your model, you have your model, and afterwards you kind of use that model in a production or prototype mode or whatever. Right? So when you have a new real-time data source, you have to prepare the data same as you did when you train your model. And you can do the batch prediction based on this data set, which was trained on the static data source, not on the new data source, right? So this is offline training because the model was trained on some offline data. Afterwards, you kind of deploy it and you use it on new data. This is like the very standard mode in which models are usually used. Okay, I see that again, people can see it. Or?
Yeah, it might be an issue with Discord, Paul. We are seeing the screen in the event recording, so for those who aren't able to see it full screen, um, we will have this posted on YouTube, so you'll be able to see after the fact, and then Paul will share the slides According to Storm Team, it does appear that you can see the slides as like a miniature preview, just not like full screen. So for those who aren't able to see for those who it's still loading for them, maybe that'll be a consolation prize or something.
Sorry, I'm really sorry to hear that.
But I think we can
It's
just
a
continue with
pity.
the talk since most people are able to see the screen.
Okay, okay, that's great. Well, let's move. Okay, so this is like kind of the introduction of batch architecture, and now I want to dive into everything and focus on the detail, right, and every piece of it. Uh, but first, let's understand why I want to focus on this batch architecture, right? So usually your initial deployment will be in batch mode. Basically, we'll use this kind of an architecture. And most of the time is enough, but let's understand the trade-offs of using it, right? So the upsides of it is that you don't really have to focus on latency and throughput. Why? Because you do your predictions offline, right? So let's move back on this slide. So you do the predictions kinda in an offline mode, and afterwards you cache the predictions into storage, and application, like the consumer application, will consume the predictions only from this storage. So basically, you decouple the consumer app and your model. And in doing so, you never, when you're scrolling your app, you never ask the model itself. You just read the predictions from the cache, right? And doing so, you don't really care so much about the speed of the inference. Otherwise, if you request directly, when you scroll your application and you request directly the model, you're very dependent on the speed of the model. And if the model is slow, then your application will be slow, then the user experience is slow, and the application is trash, right? Yeah. So this is like the biggest upside of using a batch architecture. So if you don't need to focus a lot of latency and throughput, you can focus on a working model, on a working solution that has good predictions and that can add value in its accuracy uh, uh, point of view, right? So basically, it's the fastest and easiest way to serve real-time predictions, still having good predictions, still having a good experience. And also another benefit is that you don't need a powerful machine to run 24/7 because you do the predictions, you cache them, you can close that machine. You don't need it to spin it up again, right? And the biggest downsides are that the predictions have a lag. Let's use this recommender system as an example again. Let's say that you want to cache your predictions at the daily level, right? And let's say that you do this every night at 12 o'clock a.m. Then if a new movie appears during the day, that movie won't be recommended until you recompute the predictions because uh, between these recommendations, basically between this delta of 1 day, the recommendations won't change. So you will always have lagged predictions based on what you computed the at the last time, right? And also you can generate a lot of redundant and unused predictions. Again, using this recommender system example, if you compute the recommendations for between all your users and all your items, there is a huge chance that your user won't access your applications at the daily level, right? And that means that you basically compute predictions for user that will never access them. And yeah, this is also important in terms of costs. But again, usually when you begin with a new application, your user base and item base is not that large. So again, you will kind of get away with this very easily. And yeah, so I think these are the most important things that you need to consider using this batch architecture. So now let's move to the actual architecture. So these are like the 7 steps that I will walk you through, right? So this is the diagram of the final system that you can build during the course. And these are the 7 steps that you will follow. First of all, I will explain you how to build a feature engineering pipeline. The second one is how to build the training pipeline. The third one is how to do the inference pipeline. Afterwards, how to orchestrate all this thing, because there are many moving pieces that you need to call together, right? Afterwards, you need to add a data validation and monitoring layer to basically add eyes and ears across your system. Afterwards, I will show you how to do a simple consumer app just to see how this works end to end. And in the end, you need to deploy it and add a CI/CD pipeline to actually add value and use this thing in real life. Okay, so now let's pick this one by one. So the feature engineering pipeline basically takes, as I said, the raw data. It passes through the feature engineering steps, and as an output, you have those features, right? Uh, I won't focus so much like on what kind of features you can do, because if you touched any data science project, you know that it varies a lot on your application. So, but on what I want to emphasize is you usually do these steps of cleaning your data, standardizing the data, vectorizing it, doing aggregations to call new features, to create new features, like the standard stuff. But on what I want to emphasize is that it's extremely important to version your features, because every time you ingest new data, you create a new set of features, and it's very important to version those features. So when you use those features down the line in your training pipeline and batch prediction pipeline and so on, you will always know what version of the feature you used, and based on that, you can access a lot of information, and you can always reproduce what what you're doing across your system, right? And another thing that I want to highlight is that at this step, you do the features, but you don't do the transformations. And what I mean by transformations are things like scaling your your features and so on. Why you don't want to do this? There are 2 reasons. The first one is that at this point you don't have the training and testing data set, and those transformations are always based on the split, right? So in this example of scaling your data set, you compute the scaling factors on your training data set, and afterwards you apply them on your testing data set. If you do the transformations at this step, you will introduce data leakage and many problems down the line, and you will create many problems down the line. And another issue is that you may include a lot of redundancy in your data storage, and this can be a huge problem when your data is big, because uh, basically you have the features and you have the transformations, and if you and usually those transformations are change a lot during your experimentation system process. So when you're experimenting, you want to change them many times so you can find the best set of transformations that you can actually want to use in your final product. And if you do them here, basically you will pollute your feature store with many transformations, which can grow a lot. And that's why, as a solution, instead of taking the features, transforming them, and storing them into the features like data points, you take your features and you take the function with which you want to transform your features, and you store them as such into the feature store. So when you want to ask for a transformed set of features, the feature store will know to take those features, to take the function that you associated with those features and apply them in real time. So basically, like this, you're very flexible because you have those stored features and you just need to change the function that you want to apply to it, and you can change it on the fly. And you need to store just once those set of features, right? So yeah, here are some tools that I have used and I really liked, and basically that you can use to perform these steps for feature engineering and to use for a feature store. So yeah, the next step is to take the features from the feature store to split them and create a data set. Basically, you will create the good old training, validation, and testing data set. And yeah, basically to do your training steps and to create the final model, which will be represented as a model artifact. And I realize now that I forgot to highlight what a feature store is in the first place. So long story short, a feature store is a database specialized for machine learning. It is specialized because it has these components of storing and versioning features. It can let you create, it lets you basically create tables. And when you want to ingest specific features, it lets you very easily create other virtual tables that can compose columns between all the tables between the feature store. So basically it lets you access very granular columns across the database. So you don't have to access all the table. It's very easy to access different columns from different tables and with different versions and serve them to your model. It also have capabilities of having an offline database that is usually cheap to store a lot of data but slower, and an online database that is more expensive but it's a lot faster. So basically you can use the online storage for experimenting and finding your best model, and use the online storage for serving your model and accessing your features in real time. So yeah, these are like the most important characteristics of a feature store. So as I said earlier, in this training pipeline, you have this step of experimenting where you want to find the best configuration of your model. And afterwards, using this best configuration, you train your model, and you basically, as an output, you'll have this model artifact, which at the end of the day, you will put it in a model registry, right? So in this example, the model registry is inside the feature store. A feature store doesn't really need to have a model registry, but in this case, Hopsworks, which I used in this course, has. But it's not like a characteristic very specific to a feature store, but the idea is that you take your model artifact, put it in a model registry, and again version this model, right? So when you create a new model, a new artifact, you version it, and when you consume it in the inference pipeline, you will know what version of the model you have used to do your predictions. So yeah, for training, you have the good old sklearn, PyTorch, TensorFlow, and as for machine learning platforms, I used and liked Weights and Biases, MLflow, and CometML, and there's also Neptune. I think these are the biggest players in the field. And yeah, let's go to the batch prediction pipeline. So in the batch prediction pipeline, you will use a set of features for a given version and a model artifact with a given version, right? So now you can understand why versioning your features and model artifacts is extremely important, because when you will create your final predictions, you always know on what version of the data and what model you use to create your actual predictions. So it's very easy to jump between models and data sets while you're in control, and you can always reproduce what you're doing. So there will never exist this scenario where someone accidentally changes something in your data sets or adds something extra in your data set and you rerun your process and everything breaks, right? For sure, everyone experienced this uh, this thing at some point in their career. And yeah, so you have your data, your features, and your model artifact, and you run your model on a big chunk of your data set, right? So usually another important feature of a feature store is that you can query your oops, your samples between a daytime starting and daytime ending point, right? So because usually you want to do your predictions on a data separated in time, right? So you want to query your features based on a starting and ending daytime. You take this chunk of data, which can be like thousands, tens of thousands, millions of sample points. You run your models through the sample points and you save the predictions into the bucket. And that's why this step will usually take like an hour, a few hours, depending on how much data you have and how much compute power you have. And again, for inference, you have the same tools as for training, like sklearn, PyTorch, TensorFlow. And again, usually you have your model registry into the ML platform, like weights and biases, MLflow, Comet ML. And this example in this architecture, I use the model registry from Hopsworks. And that's why you see it like this. Basically, you take the model from the feature store and do the prediction pipeline. But it's more important to understand what the model registry is than what tool you use to have a model registry, right? Okay, so one interesting step is to orchestrate all these steps because you have these three pipelines, and usually within these like big logical pipelines, you can have other smaller pipelines. For example, in the feature engineering pipeline, you will usually have a create data set step, or in the training pipeline, you have, like I said, the training for production mode where you automatically train based on the best configuration, and the hyperparameter tuning step, which you don't want to do in a automatic fashion always, because this step is very costly and time consuming, right? So the idea is that you have a lot of moving components that you need to connect between each other. And to do this, you can use tools like Airflow. And for example, Airflow connects this component into a logic component, into a mechanism called DAG, which is called a direct acyclic graph. Maybe it sounds fancy, but it is just a graph which can have only one way. But basically, acyclic graph refers to the fact that it cannot create cycles. So you just have a flow of logical steps that can go only one way without cycles. So that's a short definition of a DAG. Right, so it just basically connects multiple tasks between each other and runs them sequentially or in parallel. So yeah, now with the help of this DAG, you connect all these moving pieces, and afterwards, an orchestration tool will let you schedule this DAG to run hourly, daily, weekly, and it will also add a monitoring step on top of everything. So you can very easily access the logs of every task. You can very easily rerun on a specific task. For example, if the feature engineering and create dataset steps finish successfully and only your training step failed, you can rerun only your training step. You don't have to rerun everything from scratch, right? So it keeps this state of success and failure at the level of every task. You can also create like if branches uh, and basically take some logical steps based on the output of previous tasks and so on and so forth. So yeah, other popular tools for this step are Metaflow, Prefect, ZenML, Dexter. To be, I will be honest with you, I have used until now only Airflow, but I heard a lot of great stuff about these other tools, and I also want to test them out and see the difference. But from my experience, Airflow is the most mature one. But because it was created a while ago, yeah, it has some downsides. Okay, another interesting thing about this is how to deploy your all these components like your Oriole pipelines into a Airflow, right? Because I saw that it's very easy to create spaghetti code when you want to do this integration. So I have found this very easy way to take all your pipelines, which in the end, all these pipelines are just Python modules because you will write this in Python. And if you write them in Python, you can package them up into Python modules and post them to a PyPy repository, right? So basically, when you do pip install sklearn, you download the sklearn module from the PyPy, the official PyPy repository, and install it on your system. So you can do something very similar, and then in Airflow, every task will have its own virtual environment. So basically, in every task, you can put the name of your module, and it will be downloaded from the PyPy repository and installed in this virtual environment independently. So yeah, to do this packaging and deploying and all of this, I suggest and recommend you use Poetry, which is a Python package and dependency. Let me start this from beginning. So Poetry is a Python package manager and virtual environment manager, right? So basically, you can do Poetry add sklearn, and it's similar to pip install sklearn, and it also creates a virtual environment under the hood similar to Conda or pipenv or other virtual environment managers, and it also added this steps of letting you very easily build your Python code into a Python module and publish it into a PyPy repository with a few lines of code. So you actually just have to do Poetry build and Poetry publish to do this, to publish your code into PyPy repository. Nothing more complicated. If you don't use Poetry, it's not hard, but it's a lot of work to do this, right? So yeah, this is an interesting topic that I wanted to discuss. Oh yeah, so the fifth step is to do your data validation and ML monitoring. So those are two different things. Even if I added them into the same sections, these are two different things. So the first one, data validation. In this case, for tabular data, you have to define a data contract for your table. Basically, you will ingest data from some external source, and you want to always ensure that your data is in the right format that your system expects. Basically, this is what data validation does. So for tabular data, you want to check that the table column names are the same as you used before. Type is the same as you used before. For continuous variables, you want to check that the data range is as you expect again. For discrete values, you want to see that there aren't new values in this discrete value set, right? So basically, if until now you had only the values uh, 1, 2, or 3 in a specific column, you want to check that when you ingest new data, you still have only these values and nothing new happened. And also, you want to check for nulls. If until now that column did not had any null values, and out of the sudden it starts to have null values, it means that something happened, and you want to be aware of that. So basically, when you do this data validation, you have two options: either to raise a warning or alert, so the system will still continue working, but you will know that something changed, or you can just crash the system and it will stop working and you have to manually go and fix it. The idea is that you know that something has changed in your external data source, which you don't have control over. And the next step, the monitoring, refers mostly more to the performance of the model. So in a standard monitoring setup, like in the classic software engineering, you usually just want to see that your system is healthy, like that everything is running properly and no service crashed. But in machine learning monitoring, the problem is that your system can work perfectly, but your model started to perform poorly, right? So basically, this happens because your model was trained on a data set and your new data points start to change a lot. So the model doesn't know how to react to these new data points. So basically, it will start to perform poorly, or something, or some new data points come in that your model doesn't know how to handle, and it will just throw some random results. So basically, here you need to compute data drifts, concept drift, label drifts. If you're lucky, you can compute real-time metrics. If you have real-time ground truth, you can compute real-time metrics. In the example that I gave in the course, when you have time series, because forecasting is an autoregressive process, if you forecast, let's say, the energy levels for the next hour, after an hour passes by, you will have access to that data point. So basically, you sort of have real-time ground truth because in after a little time passes by, you can access the actual value of the energy levels and you can compute the metrics in real time. But usually this is not the case, and that's why you need to use proxy metrics. This is how they're called, those label drift for the outputs, data drift and concept drift for the inputs. And it's also good practice to always monitor the outliers, because maybe the model is still doing good, but it just had as input a new outlier which I don't know your model couldn't handle, but for most of the inputs it worked perfectly fine. So for validation, for data validations, great expectation is a great and popular tool. And for monitoring, Rise AI evidently and Seldom, from what I know, are very great tools and quite popular. But this is still a field that is maturing, so I guess we will see what happens in the next years. So as for the consumer app, I have built a classic web app that consists of a backend and front end. Basically, I exposed the predictions from the bucket. In this case, in this course, I have saved the predictions of the batch prediction pipeline in a GCS bucket. So I read those predictions into a fast API backend, and afterwards I exposed a RESTful API which was accessed later by a Streamlit dashboard. So this is something very specific. This can vary a lot depending on what web app you have. So I won't go very much to detail of why I did this because I did it just because it's just Python and it was easy for me to code it. That's the reality. But I want to highlight one thing. Why I did this RESTful API and haven't consumed the predictions directly from Streamlit. I could have done that without any issues, but by doing so, I made it future proof. So let's say that I want to get rid of this batch prediction pipeline at some point. Then it's very easy for me to swap in this RESTful API to swap consuming the predictions from a backend or from a bucket and actually hosting the model inside my Fast API server and serving the predictions real time. And by doing this swap, uh, I will keep the same interface. So basically the communication between the backend and front end will be exactly the same. The front end will not even know something changed in the implementation of the backend, right? So it's future proof in terms of this interface that will not change. So you won't need to change any clients. The communication between the clients and the server that serves the predictions will be exactly the same. And I don't think I have a lot of time, but I will try to go fast in these last steps. One quick question: how much time do I still have, so I know how fast should I go through this?
I think you can just go comfortably. We have a 15-minute cushion for the Q&A, but feel free to, you know, take as much time as you need. Maybe another like 7 to 10 minutes.
Yeah, I think that's more than enough.
Okay, perfect.
Okay, great. Yes, so as I said, the last step is to deploy this system because until now, what we did, we built our pipeline, yeah, that I kept telling you about. Afterwards, we added orchestration so we can easily run everything together. Afterwards, we added data validation and monitoring to know, as I said, to add eyes and ears across the system. Uh, last step was to build a consumer app just to see how things go end to end. And now we have to take all of this and actually put it on the cloud so people can use it, right? So what I've done, I deployed the machine learning pipeline on GCP in one single VM and the web app in another VM. I did this separation because the machine learning pipeline needs a bigger VM and more powerful VM, and the web app can stay in a very tiny and low consumption VM. And yeah, usually this is how things are separated because, as I said, your machine learning pipeline, because it's built in this batch prediction mode, doesn't even have to be online all the time. So you can reduce costs a lot by doing this separation. And the CI/CD pipeline was built with GitHub Actions. Is a great tool for any code that sits on GitHub, right? Especially if your code is public. GitHub Actions is free. You can run all those packaging, building, and everything directly on GitHub servers. So it's just great. So yeah, for the machine learning pipeline, for the CI/CD, I built the Python packages and I deployed them to the PyPy registry, right? Usually at the CI step, you also in the CI step you want to build the packages or system, and you also want to run the tests to see that your system works properly. Uh, in the course, I haven't written any tests, but this is like the good practice to do. So for CI, you build and run tests, and for CD, like continuous delivery, you take your what you have built and you push it into and you push it to be consumed down the line. In this case, into this PyPy registry. And for the web app, this is a very classic CI/CD process. You build the Docker image for the CI. Again, you run the tests using this newly built Docker image. Then you push it to a Docker registry, and after you do a rollout with your new Docker image new on the new system, on the production system. So basically for this deployment, you can use any cloud vendors such as the most popular ones, GCP, AWS, Azure, even Paperspace for like those machine learning pipelines. I recently used it and I really like it. And for the CI/CD, as I said, for smaller projects and even bigger ones that are on GitHub, I recommend GitHub Actions and even and also Jenkins and Circle CI. And yeah, and the final thing that I want to highlight is how can we take this and adapt it to an online machine learning system. So online, it means that when you make a request to the model, the predictions are computed like in real time, are not having this lag or read from a cache, and you can get the predictions in under 1 second. So you can do this very easily by having a model registry, right? So let's assume that when you call the model, the latency is under 1 second. Otherwise, you just need to optimize your model. You don't have what else to do. Either optimize your model or throw in more compute power. So you have the options to make your model faster. And architectural wise, it's quite easy to switch between those two. So basically, we had the model in the model registry, and we put it into our batch prediction pipeline, which was called by this orchestration process. To use it in a request response or streaming microservice, you just need to swap the batch prediction inference pipeline with a fast API, a backend, or a, let's say, Flink microservice. So within this microservice, you download the model artifact into this microservice, load it into your desired framework, and use it like that. So, for example, in this architecture, what we could have done is just to uh, remove this batch prediction pipeline and bucket and read the model artifact directly in our API web app. Read it directly from here. Basically, remove these two steps and put it directly here. And when the dashboard asks for new predictions, this backend will compute the predictions using our newly model, our latest model from the model registry, right? So for streaming microservices, a very similar approach. So it's quite easy to ship. After your system is built end-to-end into a batch architecture mode, it's quite easy to refine it and ship it to better modes. And what about if you want to introduce a real-time data source? So we have our user input, which requests specific data points. But until now, let's say that our model was trained only on a static data source or data sources that was gathered still in this batch mode, right? Which still has this lag. But to introduce a streaming data source, again, if you use a feature store, it's quite easy because you just have to introduce a Kafka cluster, and you will start putting the streaming data into Kafka, and using Flink, you will need this to do these 3 steps, right? So you have your string data. You will need to process your string data with Flink to standardize its format to be compatible with your current system. Afterwards, you will use another Flink microservice to take this data and put it into the feature store. So now when a new user requests data, it will still have your model which is trained on the static data source, but it will have access to real-time features, right? Basically, the features that it can access, it can be made on data that is computed in real time. And also another step that you want is to take this processed data source and store it into the static data source. So later on, I know after 1 hour, 1 day, 1 week, you can train your model on this new data source. So yeah, I guess that this was it for this webinar. So these are my socials. If you want to find me, I post almost daily on LinkedIn. I have a weekly newsletter where I talk about similar stuff as in this webinar. I also post from time to time machine learning articles on Medium, and I try to make as much as possible of my code public for people to see. And yeah, and as for resources, here is the GitHub repository where you can see everything that I presented in this course. Like everything is implemented, and you can deep down into the code. And I also have 8 lessons that will walk you step by step and give you like more concrete details and walk you through to the code step by step and explain how you can actually implement this and not keep it at the talk level, right? So yeah, that's it, and I hope we still have time for some QA.
Yes, absolutely. Thank you so much for that awesome presentation, Paul. Let me see if I can get out of this.
The pleasure was mine. I'm really sad that we have this share screening problem. It was a pity.
Yeah, sorry for everyone with the technical difficulties. Hopefully, it was still valuable. We'll definitely share the slides and the event recording after the fact, so you guys can kind of go to town. And we'll share all the links that Paul just mentioned. So, to his newsletter, to his LinkedIn, his Medium, his blog, to his GitHub. So, all the great content and resources we'll link in the in the past events channel here in the Discord. And so now we'll open it up for questions. We should have about like 5 or 10 minutes for questions. So feel free to drop those in the chat, or feel free to raise your hand and we'll pull you up on stage to ask your question.
Yeah, please. Any questions are welcome.
All right, so we've got one from N. I've gotten mostly through lesson 1, which did not require any custom coding. Will there be components that do require a bit of heavy coding, or is the project mostly about piecing all of the moving parts together? Also, just curious to know what IDE you recommend for organizing your code. So we got a few questions in there.
Yeah, so let's start with the ID because it's a shorter question. So until recently, I loved PyCharm, and I still think it's a great idea. But now I switched to this working in cloud environments. Basically, you use your ID to SSH to a cloud environment and work directly there. So, and for that, I recommend Visual Studio Code because you need the premium version of PyCharm to do that. And I have used it like 2 years ago, and I think it was pretty crappy, to be honest. Like, so if you work locally, PyCharm is a spectacular tool, but otherwise, I think Visual Studio Code, it gives you much more flexibility. In terms like finding bugs in your Python code, I still think it lacks in relative to PyCharm, but these SSH extensions are just very well made for your work. And in terms of the code, yeah, the first lesson is quite light in terms of coding because it was mostly like just taking this data and putting it into the feature store. But later down the line, like the training pipeline and the deploying everything to Airflow and so on will be more heavy on the coding part. So yeah. But uh, what I will still emphasize on is more like how these components work together and how to use all these various tools, because there are many tools that you need to know how to put together uh, to work basically as a system.
We got a question from Tang, so we'll bring him up on stage.
Hey again, Paul.
Hello.
So I'll give you some context for me. I have about a year of actual like programming experience. I just started using Python again. Originally, I used JavaScript. So if you were in my position and you were starting from scratch, would you be starting with like this type of course, or would you start with something else?
Well, I think that depends a lot on what's your end goal. Like if you want to go into data science or into machine learning engineering. If you want to go into data science, I think in the beginning this kind of course is not that useful, because basically I use some data science knowledge, but I use it because I have to, not because I know it's essential. It is not on what I focus, right?
Right.
So I use it just because, yeah, they intertwine at some point and you just can't go without it. But for machine learning engineering, I think understanding how everything works together, it's actually a good starting point. It can be a little bit difficult because there are many tools like Docker, GitHub Actions, Airflow, which might be a little bit tricky in the beginning, but at the end you will get the hang of it.
Okay, awesome. Thank you.
My pleasure.
Any more questions from the audience? So I have a couple of questions. Oh, actually, maybe a few. But I'll just pick one. So I saw you use Streamlit for your front end here, and I've seen a lot of like Python-based front end things, which is great for me who knows Python and doesn't know like JavaScript or some of the other front end tools. Do you think like these Python-based front end things are sufficient for like consumer apps? Like, do you think you could build something in Streamlit and then use it downstream to like, I don't know, for some SaaS service or something like that?
That's a great question. I think it depends a lot on the scale of your application. If you just want to build a simple dashboard and you want to ship it as a product and show it to user, I think, yeah,
Mm-hmm.
why not? Maybe I'm wrong, but down the line, I think it still uses JavaScript. So basically, it's just
Oh,
a
okay.
wrapper on top of JavaScript. I don't know about Streamlit, but I know about other tools. It's one called Dash, which is actually just a
Mm-hmm.
wrapper on top of React.
Mm-hmm.
So
Okay.
I expect that Streamlit is something very similar.
Mm.
But if you want to do something more complex, these apps are very limited,
Okay.
and you can do a lot of optimizations and many. So you're kind of limited in what you can do with them. So if you want to do something more mature and you want to do like a real product that you will know that it will grow, I don't recommend doing so.
Mm-hmm.
I saw them very practical for dashboards and yeah, very or to basically to code something very fast and to
Yeah.
do a prototype for something.
Okay, cool. So, the downside is lack of customization and maybe lack of optimization, but if you're trying to spin up something really quickly and, you know Python and maybe not some of these other front end frameworks, then it's a really good tool.
Yeah, especially if you have only Python engineers in the team is I think it's your only option, right?
Yeah. All right. Any more questions from the audience? We got end typing. Oh, here we go. Is this the place where we should be discussing the project with one another so I'm not constantly pinging you on LinkedIn? I think that's for you, Paul.
I think I think yeah. If you have any other questions, please ask.
Yeah. And I'll also call out we do have a few different channels in this Discord for people to
Oh,
interact. Oh, go ahead, Paul.
so I think I misled your question, Nigel. So if you have like random questions which you don't want to ask now, I think still LinkedIn is the better place because I try to limit my
Social
social
media.
apps and social media, yeah. And usually on LinkedIn, I'm active. In other places, I can respond to, but like in 1 week or something like that.
All right, awesome. All right, so I
Pleasure.
think that's basically it. Like I said earlier, we will post the event recording and all the relevant links and resources in the past events channel in this Discord. The video will be up also on our YouTube channel. A couple things I want to throw out there. If you enjoyed this event, we do a lot like them. So I'm going to drop a couple of links in the chat. So first is our events calendar where you can see all the upcoming events we've got. And then also, you can give your feedback on this session. And so I know we will appreciate it, and the speaker will also appreciate it as well. And so with
Yeah,
that,
I will.
yeah, absolutely.
Uh,
Thanks,
yeah,
Paul.
any constructive advice, it will be really appreciated. Like I know I'm not the greatest speaker out there, so anything you think of, please say.
Well, I think it was a fantastic workshop. All right. Well, thanks again, Paul. Thank you for the audience for joining. And our next event will be a workshop all about data strategy. So we've got that coming up in a couple weeks. So be sure to stick around for that one. All right. Thanks, everyone.